Okay, good afternoon, everybody. So great to be here. So today I'll be presenting work that we did in IBM Research on detecting anomalous runtime behavior in distributed cloud applications. So my co-authors, Atri, Mandal, yeah, he's here. Shubham, are you here? Okay, looks like Shubham is not here. So, and my other two colleagues, Gargi and Shubhajit, they couldn't make it to the conference for some other commitments. Okay, so what are we trying to solve here, right? So the use case that we had is diagnosing distributed applications. So the main cause of failures in distributed applications is, when the transaction flow path, right? Whenever you make an API request to an application, that service call is basically results in a lot of function calls and including remote procedural calls to different modules and microservices in the application, right? For example, here what I show is the flow 1, flow 2, flow 3, and flow 4 are 4 top-level API calls to the application, right? And there are different microservices that are composed together to serve this application. And for each such API call, it flows through certain nodes or function paths within that individual microservice, or it could even make a remote procedural call to a different module, okay? Now, most of the time what happens is, whenever there is a misconfiguration or a bug in the distributed application, this transaction flow path gets interrupted at some point, okay? Now, what we are trying to solve in this work is, when your top-level API call is not working, we want to give you the insight as to where in this entire graph, or what we call as the control flow graph, the problem is, okay? So in particular, at which node did the function call or the transaction flow got interrupted? So the classical way of how this is done today, okay, is using a combination of metrics and logs, right? So metrics, as you know, is like basically people track a bunch of SLA metrics, like the number of requests a particular module is serving, or the response time, et cetera. And whenever you see that metric dropping below the SLA requirements, what you do is, the admins of that team of that application basically go and pull out the logs from the different modules and the different microservices, and they kind of sift through the logs manually to figure out where the problem is. So this is a very painful exercise, right? And this is exactly the thing that we are trying to automate in this work, okay? So this kind of data mining model that we have built in this work will automatically pinpoint where the problem is. So what do people look for in the logs, right? The one obvious thing that will come to your mind is errors and warnings, right? But the story is not that simple. The reason is there are several times when these warnings are benign, right? There's some warnings you'll see being printed even though the application is working fine, right? And the reverse is also true, which are several times errors don't manifest as warnings or error messages, right? So just looking at errors and warning messages will not tell you where the problem is. So you need to look at the logs, right? So what we are again trying to do is, using data mining, right, we are planning to collect all the logs from the different microservices and automatically infer this distributed control flow graph, right? And how we do that, right, in a scalable way in the presence of, the logs of the different applications being interleaved, as well as the same application being multi-threaded, et cetera, is the focus of this work. So, okay, this I can skip. Yeah. So coming back to control flow graph, right? So this graph, as I said, composes of nodes and edges. So these nodes are nothing but manifestations of the print statements in the source code, right? And these edges are essentially these function calls or remote procedural calls for that matter. And this is just a dummy example of an if-then-else clause, right? But in reality, these control flow graphs can look pretty complex. And this is like from a real control flow graph that we mined in one of our data sets. So let's take a look at why this problem is challenging and give you a feel of the data set, right? So what I show here on the top is a small snippet of a control flow graph with 4 print statements, right, T1 to T4. And what I show is different flows growing through that portion of the control flow graph. And below is basically the resulting logs that are being generated, right? So there are two key things that I want to point out in these logs. The first thing is different executions through the same print statement result in log lines which kind of look similar, but they're not identical. And the reason for that is when it's executed, the parameters are embedded, and you see different parameter values for that same print statement, right? So the P placeholder for the parameter there is replaced by different parameter values. So the lines kind of look similar, they are not identical. That's one takeaway. The second thing is these transactions, as I told you, in a distributed application, right, they are all interleaved, right? And not only again, across microservices, even within the same microservice. For example, flow 1 and flow 4, which are highlighted in red and blue, do not happen consecutively here, but they are interleaved, right? So essentially what you see is two kinds of problems. One is even mining the print statements from the logs is a hard problem because they don't look identical, but it's some version of a clustering problem, and I'll tell you why it's challenging. The second is mining these edges between nodes, right, is some version of a sequence mining problem. But again, I'll tell you why classical sequence mining problems cannot solve this problem, okay? So let's get to that. So why the mining of print statements, right, or the clustering problem is not trivial, okay? I'll show an illustration of this in the next line, is that these parameter values can be pretty arbitrary, okay? We are making no assumption about the application at hand, right? So these parameter values could be, pretty much, they could be, unstructured parameters of any pattern, right? They could be long parameters. And the consequence of that is the same print statement can look very different in two log lines, okay? So if you run some version of a clustering algorithm with like an edit distance based text similarity metric, these two print statements, these two log lines will not end up in the same cluster. So essentially, you will mine like two different print statements for the same actual print statement. So we call it a fragmented cluster, right? The other version is the reverse, right? Which is two different print statements because of a common shared parameter, right? In this case, the print statement here, right? If you see the job request, right? So that's like a huge parameter, right? Which is common across both these two print statements below. But they are actually different print statements. If you see the first part, right? One says preparing response, the other says synchronized response. So if you run some version of a clustering problem, what will happen is these two will get clubbed to the same cluster, and you'll infer a wrong print statement, right? So this is why classical clustering based on a text similarity metric does not work here. Now let's take a look at what is our solution approach to overcome this problem. I'll come to the sequence mining after this, okay? So at a very high level, what we essentially do is, instead of just leveraging the text signal, okay, what we leverage is the multimodal signal of what precedes and what comes after each log line. So the basic intuition is this, right? If you see two lines which are kind of similar, and they are always preceded and succeeded by similar looking lines, then you can do a joint classification of that log line to the desired print statement cluster, okay? So that is the key idea that I want you all to take away with. A lot of details are in the paper as to how you do it, but at a very high level, the other thing we do is the sheer volume of logs, right? In this application domain, we are talking of terabytes of data a day, right? So even running like a simple clustering algorithm, right, on raw log lines just doesn't work. So what we do is we convert this raw logs to an intermediate data which we call as approximate templates, right? And we have some tricks of how to do that using some heuristics. And because it's heuristic based, we get some approximate templates. And remember, this is just an intermediate step, right? Given that it's approximate templates, and we know it is approximate for a genuine reason, what we then do is we use like, scalable, edit distance based clustering to get some kind of refined text clusters. But again, as we said, even that is not enough because of the limitations I discussed before. And then what we do is we infer the predecessors and successors, and then do a multimodal joint classification to get the clusters. Okay? So this is the high-level overview of the clustering part of the pipeline. Okay? Again, details in the paper, but I just want to kind of give you a sense of the overall solution. So again, there are some caveats with this, right? Which is, as I told you, the sequence mining problem itself is kind of non-trivial because of the interleaved logs. So any errors that you get in the sequence mining can affect these results because you use that feedback of the predecessors and successors in this joint classification, right? So for example, if you compare it with just a pure edit distance based clustering, which doesn't use any kind of sequence information, errors in the sequence mining part of the pipeline will not affect that, right? Whereas here, for obvious reasons, it will, right? So let's come to sequence mining. And again, here the intention is to give you a sense of why it's a new problem and what is our solution approach and not the details, right? So in sequence mining, right, I mean, frequent item set mining and sequence mining is a very well-studied problem in the data mining community, right? So what's different here, right? So what is different here is that we have interleaved logs, okay? If you remember, people who have studied this FIMs and things like that, right? Prefix span, sequence mining, and all those, right? So the input data model, the model, the abstraction is that of a transaction database where you have each delineated or separate transactions. So for example, a particular transaction ID, you'll know it went through state or this print statement, like this followed by this, followed by this, right? And you have multiple such rows corresponding to each transaction. But then remember that in our case, right, we are trying to solve it for generic cloud applications where these, in many cases, right, I mean, you cannot even have like a thread ID because there are remote procedural calls, right? So there is nothing like, you do not have transactions in front of you, right? You have interleaved logs across all API calls that are coming to the application. So all I'm trying to get at is the abstraction of sequence mining has a prerequisite of transaction IDs and clearly delineated transactions, which you do not have in this case. So classical sequence mining doesn't apply to a problem. So however, we can leverage some ideas from it, and I'll tell you where it breaks and how we fix it, right? So in classical sequence mining, right, I mean, basically the key insight is you look enough of the data stream, right, and you see who follows what. But the only difference here is, as I said, let's take the template T2, which is nothing but the print statement. Template is the other word we use for it. The next immediate line in the log, although the reality is this CFG where T2 is followed by either T3 or T6, right? What you see in the log is it's followed by some other log line, which is basically a noise because of multi-threading or interleaving across multi-services, right? So instead, what we do is we cannot rely on the immediate next line, but let's say if we look ahead, right? We look ahead up to some portion, and we keep doing this over the entire data stream for some portion of time. And then you keep track of these counters, right? Then essentially you'll get a signal that T2 is followed by T3 quite a few number of times, right? But the problem with this approach is you do not know how much to look ahead, right? What you'll end up is you'll also find high values for counters which are not to the immediate descendants, but also to the downstream descendants, right? Like you'll have a counter from T2 all the way to even T9, which is like right at the bottom here, right? So the point is because you do not know how much to look ahead and you do not have transaction IDs, you will not only mine these edges, immediate successor edges, but all the way to the downstream descendants, right? And then what you need to do is you will find like a superset of the CFG, and then some of you who have worked on graph algorithms will say, hey, run transitive edge reduction, right? Yeah, sure, you can run, and we have evaluated against that. But the problem with that is in these practical cloud applications, right, detour paths are very practical. And they happen for almost 25% of the time, which is what I mean by a detour path is there is some edge like this, right? And there could be a genuine edge from T2 to T9 by a different path, right? So if you do transitive edge reduction, by definition, you're removing those edges, right? So that doesn't work either. So a gist of our solution approach, right? So the high-level approach for a solution is because of interleaving, right? The key problem that is happening is you do not know the next line is a genuine successor or is some random log line because of interleaving. That's the genuine reason why you're struggling with this problem, right? So what we do is, we break this up sequence mining into two phases, right? The first phase, we try to mine what is called nearest neighbor groups, and all of you are familiar with that, right? So nearest neighbor groups is essentially, I look at enough of this data stream and mine groups of people or templates or print statements in this case, which are always typically found to be together, meaning they are correlated essentially, right? Now, once I get that information, when I see this log stream, right, for example, for T1, if I mine the nearest neighbor groups, right, if the next immediate, the succeeding line after that print statement is not part of the nearest neighbor group, then I know it's because of noise, right? So the benefit of doing this in two phases, if I first mine the nearest neighbor groups, when I'm running this algorithm of incrementing counters, all I do is whenever I see a template, for example, T2, I skip the succeeding candidates who are not part of the nearest neighbor group. So I just skip the counters of those, the first entity which is member of the nearest neighbor group. So what that gives you is, you are not forming edges to the noisy candidates, right? You are forming an edge to a genuine candidate, and that too to an immediate successor, not to the downstream descendant, okay? So at a very high level, we break this into two phases, which makes it work. And with nearest neighbors, just a point here, you're all aware of this algorithm, right? So what we do over here is, to trigger this algorithm, we convert this data into an intermediate model, and this is kind of interesting. We take the log data, we mine these clusters, and then for each cluster, we find the instances where that cluster instance occurred, right? And we get a time series per cluster, essentially. So for each print statement cluster, we get a time series, okay? And then what we do is, once you have this time series, what you can see in this diagram is, this CFG, or this control flow graph, essentially has these three building blocks, right? There are linear sequences, like T1 is always followed by T2, or there are these forks, where T2 is followed by either T4 or T5, right? Or these merges, right, wherein T5 has either T2 or T3 as the predecessor. And what can be shown is, depending on this structure of these sub-modules, the time series correlation or the time series looks accordingly, right? For example, linear sequence, T2 is nothing but a slight right shift of T1, right? And similarly, where you can see from T2 and T4, they will have substantial overlap, if not full, and so on, right? So the key point I'm trying to say is, by converting into this intermediate model of the time series per template cluster, and given the different types of sub-blocks or modules in that CFG, which is sequences, forks, and merges, we throw in different time series correlation algorithms to mine these substructures, okay? And that gives us the edges, okay? With that, I will now move to the results. But before I move to the results, the one thing I wanted to say is, this entire pipeline that we had, right? Essentially, right, it goes like, because of scalability, we first mine approximate templates. Then we cluster those approximate templates using a scalable LSH-based, LSH is this locality-sensitive hashing, right? Scalable, way of edit distance to form approximate template clusters. Then we form the nearest neighbor groups. Then using the nearest neighbor groups, we mine the edges. And then using this predecessors and successors of these approximate template clusters, we refine the templates using this multimodal joint signal to form the accurate CFG or the print statements, okay? So that's roughly the high-level pipeline. And in today's world, right, as I said, especially for this application where we are talking of terabytes of data a day, we made sure that, this entire pipeline can be, distributed, right, organically or horizontally scaled, what I mean. Like if you throw me, instead of terabyte a day, a petabyte a day, I will throw in 1000x more machines, and this thing will work, right? And we built this whole pipeline on top of Apache Spark. I'm sure you all are aware of it, right? And had distributed versions of all these algorithms, okay? The details are in the paper. And once we mine the CFG, right, anomaly detection is very trivial. It's basically deltas or diffs in this CFG. Like if you have mined a particular CFG, and then suddenly you see that one edge is not present, right? Or the probability, the branching probability that we infer has changed from 70-25 to like 10%, 90%, right? These are all kinds. So any kind of deviation from the mined CFG is like an anomaly. And based on the type of deviation, we have different classes of anomalies, right? And you can look up our paper on the different types. And we had a full architecture on an end-to-end system, right, where we collect these logs from the cloud machines using Logstash adapters. It goes to something called a pub sub called Kafka. Then the logs are ingested into Elasticsearch, and then it's a Spark Hadoop-based offline pipeline where we build these templates and these, the CFG graph. And then we consult these training models in real time to do anomaly detection, okay? In the evaluation, again, we are running out of time. I just have something like 3 minutes. So the key points are this, right? We evaluated against, the one main point I want to cover here, right, in terms of evaluation. We had to evaluate against data sets, right? The problem we had with real data sets is we didn't know what was the ground truth, right? We didn't know how the real CFG structure looked, because in most of these third-party microservices, we didn't have source code, neither the binaries. So Shubham, right, who is here, right, he was an intern. He worked with us to build an awesome synthetic log generator, which models all types of programming constructs, right? And it has essentially these phases of constructing these different types of graph structures. Then within each parameter node, which is the print statement, it models different types of parameter usages, like long parameters, short parameters, where they occur, what fraction they occur, et cetera. And of course, the execution model, which is a multi-threaded model on this, on a single microservice, multi-microservices, and so on. And then again, we evaluated this against the synthetic and real data sets. And real data sets, we used like 3 or 4. Like one is the Linux syslogs. And then one thing which I want to highlight here is we use this OpenStack. Actually, these results I'll skip. These are like individual results for the template mining, the edge mining, the sequence mining, and the anomaly detection. And what I'll instead show you is, let's just show you this OpenStack, right? We evaluated this entire end-to-end system on this OpenStack system, which is the VM provisioning system you're aware of. It composes of multiple microservices. And whenever you give like a create VM request, there are a lot of transaction flows across the microservices to make that VM happen, right? And what we mined is this control flow graph from there. This is just a summary version, and it shows you how that exact template looks. It was like a graph with 300 nodes and many edges and so on. And we actually killed a process, right? And the create VM failed, not surprisingly, right? But the value value add of our approach was we could exactly pinpoint where in that flow it got disrupted. And we identified that exact process that was killed, like the template that was highlighted, okay? And these are our Spark results, like where we increase the number of Spark workers, and we show that the execution time dropped. And the key takeaway here is even like on a 10 VM, low-end VM cluster, we had like 500 GB a day throughput. With that, I will conclude to the main takeaways, okay? And just before that, this is the application on top of the OpenStack where we show these, Elasticsearch, sorry, where we show the anomalies, yeah. And so the conclusions, right? So I'll just take iterate on the 3 main takeaways. So what we showed is to diagnose distributed applications, we proposed a model of mining a control flow graph and then detecting deviations in this graph to pinpoint anomalies. Then how we did this, why this was challenging was because of interleaved logs and because of parameters. And we told you why classical algorithms for clustering and sequence mining don't apply. And we proposed new algorithms. And lastly, we showed that our algorithms do better than prior state of the art, which doesn't directly apply in these cases. With that, I'll be happy to take questions. Yeah.
Hi, thank you. Very, very interesting.
Thanks.
I guess I have 2 questions that are maybe the same question. One is, sometimes you have crazy things happen in programs that are not observed. So I would think that you would have situations where you really can't connect it to there's no neighborhood.
True. Yeah, true. So basically, yeah, good question. So all we can see, it's a matter of granularity, right? So depending on how extensive your logging is, we can just pinpoint till that portion. So for example, between 2 print statements, right, which is what we observe, if there is something where it went wrong, we cannot pinpoint you at that granularity, right? But still, it is much better than pinpointing at, hey, this microservice failed.
Sure. The other question I have is, how do you handle when the code changes? and the code path changes?
Ah,
You
okay,
have to retrain?
that's great question. So actually, that is some follow work we are doing right now, where we study the evolution of this CFG when the source code changes, and it brings around many of these interesting questions of is the anomaly due to a genuine code path change or something? But as of now, our current, it's, as I said, it's work in progress. But what we observed is for that, it seems like we need to have access to a DevOps ecosystem where the source code is also there to simultaneously see changes in the source code. Without that, I don't think we can differentiate between like a real anomaly versus suddenly a new code path was introduced.
Another question?
Question, if you had a choice to talk to people developing a new system and you said, hey, you could do your logging better and it'd make it much easier to tracking.
Okay.
If you had that luxury
Yeah.
to tell them what a new best practice is, what would you say?
Okay, perfect. I think you have a great question, and that was one thing I didn't get time to. It was in the slide though. So you know about New Relics and App Dynamics. There are a few startups on these. So basically, what they do is they instrument specifically a transaction ID, okay, within function calls of the same microservice, and also across microservices, assuming it is JVM bytecode, they do some hacks and stuff like that. Okay. So bottom line is, if you instrument like a transaction ID for each flow path explicitly, right? That will simplify many of these issues, right? The anti-sequence mining thing, you can just use that transaction ID. There are systems like papers like Xtrace, then Magpie, then Google has a system called Dapper. There's like a bunch of systems which embed transaction IDs. But again, the problem is in this cloud ecosystem, most of the cases, you don't have that luxury of modifying third-party microservices.
Anyone else? Okay, then thank our speaker again.
Thanks.